Let's get started. All right. Yeah, we've got a good crowd today. So first of all, thank you very much today, everyone taking your time out of your schedules, wherever you are, to attend our webinar. My name's Bob Fung. I am the Director of Marketing at NETINT Technologies. I'm going to be the host today. So I'll keep the introduction short because I think Sean and Mark got a lot to talk about today. But basically, the title for today's webinar is ASIC Video Encoding in the Cloud. And presenting that today is going to be, change my slide here. Mark Donnigan, the Head of Strategic Marketing at NETINT, and Sean Varley, the Senior Solutions Director at Ampere Computing. Today's webinar, we're going to focus on showing you some of the advantages of combining ARM-based servers and ASICs for streaming video applications. So basically, Mark and Sean will present, and then we'll discuss any questions that you may have afterwards. So if you do have any questions that kind of come to mind during the presentation, use the little Q&A feature in the meeting controls, and you can just put your questions in there, and we'll do our best to answer them. So with those introductions out of the way, Mark, I will stop sharing, and I'm going to hand it off to you.
Okay, awesome. Okay, here we go. Everybody can see this?
Yes. Yep, you can see it.
Good. All right. Awesome. Okay. Well, good. Well, so we're here today to talk about really three numbers, and that is 10x, 18x, and 180x. Now, let me set the stage. And first of all, we purposefully have kept this presentation somewhat short. So we're going to try and, keep this in the 25-minute, maybe 30-minute window. That has a lot of advantages. I think, we all have sat on way too many webinars and events that have gone maybe a little too long. The downside to that is that there's no doubt we're going to, breeze over some information or not even cover something that might be very relevant to you, or you want to learn more about, or you're like, wait a second, I don't quite understand that, or tell me more. So as Bob said, please don't be shy to either enter questions in the Q&A or just in the chat, or at the end, we're going to open it up, and we're happy to, the floor is yours basically. So we'll be happy to address as much as we can. But let's jump in here, starting with we're here to talk about the incredible advantage of video encoding when it's performed with ASICs, a whole new architecture that is an ASIC video transcoder that is hosted in an ARM-based server. So I think we all can remember the black boxes of fixed function hardware encoders that normally, when you would reference hardware video encoding, the thinking was, okay, it's a black box. Basically, the functionality and performance that I got on day one when I first installed it is going to be the same, as 7 years later when I decommission it. There is a real new architecture, and that is what we're here to talk about today, that really combines the best of hardware, the best of hardware acceleration, silicon with software, so you get the flexibility and the benefits of CPU, software-based encoding, with the massive advantage of purpose-built silicon. And it gives you a 10x advantage. And so we're going to show you the numbers around this. You're going to see some real data. And if we look at just compared to X264, it's actually an 18x advantage. Now, you might be wondering, what is FPS per watt? Obviously, everyone knows what FPS is, frames per second. But it's our observation, and for some of you, if you're working in hyperscale environments, if you're working in very, very massive video operations, large platforms, clearly that energy efficiency is really now coming front and center. And certainly in the data center, it's no secret that there's increasing pressure on carbon neutral and just all of these initiatives. And so it's our observation, and in working with a lot of the hyperscale platforms literally around the world, we're seeing that people are starting to think almost in terms of this frames per second per watt. So again, we're going to show you the advantage here. And on X26 or for H.264, but we tested with X.264, it's an 18x advantage over running the same CPU that's hosting the NETINT ASIC transcoder versus just running it on CPU. So massive. And of course, for HEVC, with X.265, it's like 180x. So it's very, very significant. So for those that don't know who NETINT is, I'll keep this very short, but we were founded in 2015, and the company was founded to build a next generation ASIC purpose-built technology for video transcoding and processing. Very senior team. We have over 100 now silicon engineers that are headquartered. We have an R&D center in Toronto. We have an R&D center, and our headquarters are in Vancouver, and we have a very strong group of engineers in Shanghai as well. Our architects are highly experienced, and the team comes from Qualcomm, Broadcom, PMC. You can read, AMD. You can read the logos there. So the point is that we are a team of silicon SoC ASIC experts that have really come together to pioneer what we believe is the next generation of very high performing video encoding solutions. So let's talk about our first ASIC. And this is the G4, the Codensity G4. This is at the heart of all of our VPU solutions. So we actually are not in the chip business. So you actually are not able to buy the G4 and then build that into your own solutions. Our business is not selling to OEMs or to system integrators. We take this solution, this ASIC, and we build that into our solutions. And in the next two slides, I'll show you what those are. But this chip, the G4, has an H.264 and HEVC video decoding and encoding engine built into it, includes a PCIe 4.0 interface, in fact, a 4-channel interface, so we get extremely high both throughput and extremely low latency. One of the things that we'll probably even do a webinar around is the latency performance. This really is an ideal solution if you're building mobile cloud gaming workflows, virtual desktop, anything where you need literally 20, 30 milliseconds of end-to-end latency. This is the solution for you. We include an NVME interface, and we'll be talking some more about that, why that's so valuable. And it also has on-chip advanced video algorithm support. There is an area on this silicon that can actually run some AI and ML algorithms, for region of interest, advanced rate control. There's some very interesting applications, and that is all included on the G4. Now, there are two products that we have commercialized, meaning that we've taken the G4 and then built it into a solution that you can then install in a server in a data center. The first one, and the one that we're mostly going to be talking about today, in fact, really exclusively talking about today, is this one, the T408. And you'll notice it looks like an SSD drive. The same form factor, it's a U.2 module. Literally, if you have a server with all of the NVMe U.2 slots accessible right from the front, you don't even have to unrack the server to upgrade your entire encoding operation from software to ASIC to this solution. And so the T408 has one encode and one decode pipeline. It's capable of encoding or transcoding, because you can obviously process multiple streams or files simultaneously, and that gives you basically 240 frames per second at 1080p, or up to one 4K P60. So of course you can do the math to figure out, if you're wanting to transcode an ABR ladder, how many profiles you might be able to get based on what your renditions are. What's beautiful about how we design this is that the host CPU load is extremely low. There's just really a few threads, and I purposefully wrote a few. That's not, like a few means 10. That's literally a few. 2 or 3, maybe 4 threads are required at most on the host CPU, and you're going to see in some of the data here in a few minutes what that looks like. Just really, really remarkable. So you can have a server fully loaded with, for example, T408s, and it could be transcoding 100 streams or more, depending on resolution and all. And that server might only be running at 20 or 30% CPU load, which is amazing. It consumes 7 watts at full load, so it's incredibly energy efficient, and that translates to about 3/4 of a watt per 1080p stream. Very easy integration with FFmpeg and really any other transcoding or media processing pipelines. So if you built your own transcoder, or you have some combination of a commercial solution and something you've customized, this can be fully integrated. We have a very strong API set around it, and have a lot of experience integrating these. The next version is called the T432, and you can clearly see this is a standard, add-in card, AIC, PCIe form factor. This includes 4 of the G4s. So basically, this just gives you 4 of the T408s, and it's very, very dense. This consumes 27 watts of power, and again, the same 3/4 of a watt, 0.75 watts per 1080p stream, all the same integration, except that now you can get 960 frames per second from a single card at 1080p, or 4 4K P60 streams simultaneous. I'll make a quick comment about some of the performance and for those of you that are familiar with ASICs, then you know this, but if you've not had the opportunity to work with ASICs or with silicon, one of the massive advantages is unlike software and CPU-based solutions that don't always scale linearly, silicon does. So when it says 960 frames per second, that is 960 frames per second, regardless of codec, regardless of load. There isn't, that's not sort of if I twist all of the knobs and the dials the right way in terms of getting my system calibrated or just tuned, then I can get that. So that's one of the things just to be aware when we're throwing out some of these numbers. If you're thinking in the back of your head, yeah, but what about this scenario? What about that scenario? Under full load, these numbers hold up, and that's a massive benefit of ASICs. So I'd like to flip it over to Sean right now, who's going to share about Ampere. Sean, did we lose you? Did we lose Sean? Okay, Bob?
I can take it if Sean is
Sorry,
technical difficulties.
Okay, yeah, yeah, go ahead, jump in.
Sure.
Thanks.
And Sean,
Thanks,
Sean, if you get your audio fixed, let me know. So my name is Darren Vallis. I'm a senior director FAE at Ampere Computing, and I've been working to support NETINT. And I'm just going to give you a very quick overview of Ampere's advantages. So our SoCs have been architected from the ground up for cloud-based performance. And really, we focused on three things: predictable performance, scalability, and power efficiency. So that means from the ground up, our SoCs were designed and architected with that in mind. It means that we've chosen to scale out our cores to a large number of cores. Currently, we have an Ultra processor that will run up to 80 cores, and an Ultra Max that goes up to 128 cores. The key thing about this is, though, that it can run all cores at maximum frequency sustained. So we are really, really going for predictable performance for cloud-based workloads. This lets us give the highest density of cores per rack to customers, and we also design it with a lot of PCIe I/O. We have 128 lanes of PCIe per SoC, regardless of our SKU, from 32 cores all the way up to 128. And finally, taking advantage of that, we're able to start from a clean slate and design our SoCs so that to focus on power efficiency. So we have leadership in power per core, and wrapped around that is advanced system and power management. So that's an overview of the SoC. Right, so basically just summarizing what we were just talking about, the three tenets. Predictable performance means that your workloads can have a consistent performance for customers. We have linear scaling, meaning that if you increase the number of cores running workloads, let's say from 32 to 80 to 128 or more, our performance scales linearly. You can get, if you run a workload and get X amount of work out of one core, you'll get 80X the amount of work out of the entire processor with 80 cores or 128 cores. And we've seen this demonstrated time and again at customers, especially like with CDN-ish workloads or many others. And obviously your mileage may vary. If your workload is highly biased towards single-threaded or something, that won't be the case. But we find that by and large, cloud-based workloads scale very well. And then finally, power per core. Our designers are really focused on power efficiency as opposed to give me the maximum amount of performance per core. So we have very performant cores, but they're very performant as well as being power efficient. So what this leads to is consistent performance for your workloads, scalability for your workloads, and essentially getting more work out of the same number of racks in your data center. And next.
That's great. Thanks, Darren. Let's see here. There we go. Oh, advancing. Okay. Yeah. Thank you, Darren. So I think it's really easy to see why the combination of an ASIC dedicated to the video encoding and transcoding function running on an ARM-based server is super, super compelling. So, let's get into the data. We're going to show you over the next 3 slides. Now we decided to focus or just show you the data on H.264. Again, we fully support HEVC. Part of the reason why we're showing you the H.264 data is that this is the best case for CPU. Obviously, X264 is, an incredibly efficient and incredibly optimized solution. It's not as advanced a codec, so it runs faster. HEVC, the advantages that we show you here get even larger. In some cases, just overwhelming difference. So, in case you're wondering why we're not showing HEVC numbers, it's really because we wanted to just give the best case to the CPU, just to show show you just how tremendous an advantage this solution is. So let's start out and look at decode performance. And what you're looking at here is, you know, on the y-axis, as you can clearly see, is the total frames per second coming out of the system. This is an Ampere Altra Q80-30, and so this is 80 cores. And this particular chassis was loaded with 20 T408s. So of the next 3 slides, it's all the same configuration, 20 T408s running on the same Ampere processor, SoCs, and chassis. And so what we see here is that the red line is just the tracking of the frames per second per core. So going from 0 to 80, of course, on the x-axis there. And you can see that it actually scales really pretty linearly on CPU. For decode, CPU works pretty well. What's interesting is that right at about 40 cores is where the advantage actually tilts for decoding. Now, this is decoding only to CPU in terms of scaling. Now, you can say, yeah, but that means that, you know, if I'm running less than 10 cores to actually maintain the operations of the T408s, then I can be doing a lot of other work on the CPU, and that's exactly right. So the code density, the T408, as you can see over on the right there, definitely has a power advantage in that the T408s consume 0.9 watts per stream, so just under 1 watt per stream. And for the pure CPU, it's more than double. It's like, you know, almost 2.5 times. So 2.2 watts per stream. And this is for decode performance. Now, let's look at transcode performance. This is where it gets really, really interesting. So what we did here is using FFmpeg, we transcoded a 1080p 24 stream to 720p 24. Made sure that we were producing comparable quality. So this was subjectively viewed, so visual inspection, and obviously using X264 for the software comparison. And so if we look at the software only results, also, let me explain the encoder configuration, because some of you will definitely want to know what that was. So we set it up at a CRF23 and speed medium for X264. Totally get that for some applications, this would be low quality or lower quality than you might desire. And maybe for other applications, this would even be higher quality. But, you know, this was where we decided to go ahead and set it up. Now, one important point I want to make also here is that unlike, for those who are familiar with some of the older fixed function, you know, I'll call them the black box hardware encoders, where really there was virtually no ability to adjust or to calibrate or to determine video quality. You basically, it did what it did. And either you liked it or you didn't, but it did what it did. You had very little ability. So with our solutions, we absolutely have the ability to produce extremely high, better than broadcast quality. And if it's in an application where it's user generated or where there's just not the need for that, and you want to tune the encoder for something different, you can do that as well. So I just want to make that observation, because for those of you that are familiar with X264, you might say, well, medium is, you know, not bad, but it's not that good either. We can absolutely produce quality that's consistent with slow. So let's go back to looking at transcode performance. So again, on the y-axis here, we have total frames per second of the system. We have cores on the x-axis, as you can see. And you can see the CPU, you know, it scales to 560 total frames per second across the whole machine. So it's about 7 frames per second that each core is able to transcode with these settings. And that's just running X264, 100% CPU. Now, when we activate the T408s, well, the number skyrockets. 4,800 cores, almost, or I'm sorry, frames per second, almost 5,000. And what's super incredible here is that fewer than 10 So just a little more than I guess about 15% of the server is required to reach full performance. So again, the point is that you're able to free up all those CPU cycles, those extra CPU cycles for packaging, for DRM, for other things that you might want or need to do. Really, really compelling. As I stated, for those of you that are working in HEVC, well, the advantage just gets, because the beautiful thing is that our results don't change. So for the HEVC codec, it's still 4,800 frames, but the CPU, of course, is going to take a huge hit. It's not going to be able to produce 560 frames per second. So yeah, it's very remarkable. Now, I mentioned that we are looking at a whole new way to really measure and to look at energy efficiency, and that is performance per watt. And so here's a graph that is very interesting that just shows literally the power consumption, frames per second per watt. And the way that the numbers shake out is that the chassis and the CPUs consume 130 watts. The T408s consume 140 watts. And so it's 270 watts total. And again, we already saw the number 4,800 frames per second. And that translates to 17.8, just shy of 18 frames per second per watt, whereas the CPU is bouncing right around about 1 frame per second per watt. So you'll remember the 18x number. This is exactly where the 18x number comes from. And if we go back to this slide, you will recall the 10x number, and you might say, yeah, but Mark, you're not exactly 10x, so I get it, you're rounding, but it's not quite 10x. Well, the fact of the matter is that because you need a network interface card and there's some other things that we have to put in this, we're not able to add the extra cards into this chassis that would give us the full 10x. But it is a 10x advantage here in density. And then here's where we get the 18x. And maybe in another webinar, we'll show the performance on advanced codecs like HEVC and perhaps even AV1, which is coming. And I can imagine somebody's going to ask about that. Super compelling. So Sean, I see you're on.
I'm back. Can you hear me?
All right, we can hear you. So hey, welcome back. Why don't you present our reference design?
Yeah. Thanks for the handoff, and thank you also to Darren earlier. I could hear him do the diving catch. I couldn't say anything. But no, technical difficulties on my end with the Zoom client, so apologize for that to everyone. Let's talk about the reference design. So Ampere and Net have been working together for quite some time, doing a lot of these sort of benchmark exercises that Mark walked through. And as we kind of did a lot of this, we sort of scratched our head and said, hey, this is a pretty compelling reference design for both data center and edge applications. To really do very, very dense video transcode, and especially with the complex operations like the transcode operations that Mark was showing earlier. This is a really, really compelling product or reference design. And so what we're showing here is the Ampere Altra Q8030, which is our 80-core, 3 gigahertz, really popular SKU in our what we call Mount Snow 1-socket 2U reference chassis. Mount Snow has slots for up to 24 actually U.2 drives, but if you need networking, which most people do, you actually kind of need to take a couple of those slots back for that networking. So in this particular reference design, we're really kind of thinking 20 co-density 408s inside this 2U chassis with the 1-socket Ultra yields all of the performance that Mark just showed, up to 4,800 frames per second in transcode and 160 streams at 1080 30. So this is a really, really compelling dense transcode design. The nice thing about the Ampere Altra processor, which I'm sure that Darren did a very, very eloquent job of stating, is that it's a very highly predictable platform. Ultra, for many things, gives you very, very consistent latencies, no matter what the application is. It's just part of our design and our philosophy in building processors. This yields low latency, very, very consistent P99 latencies across processes. And this, of course, then delivers you very, very high quality transcoding. And of course, all of the low power design that went into Ampere Altra, you're benefiting from. You saw the power numbers in the last slide. This is a really compelling platform, whether you're doing this, in bulk in data centers or patching it in at the edge. This is a super, neat reference design. It can be purchased through our platform partners, and if you're curious, I'm sure that we would love to hear from you after the webinar. So I'll pass it back to Mark.
All right, thanks, Sean. Yeah, you definitely will want to check this out. This is absolutely worth benchmarking. So we are going to make a special offer today for those of you who have taken time out of your day to to listen in and learn about what we're doing. And look, we being video people ourselves, we know that there's a lot of claims made out there in the market. You hear everybody is saying, their solution is the best, but until you get your hands on it, it's hard to be able to really know if the claims are true. And so we decided to put together an offer for $249 to buy a T408, and this is a fully functional. This is not sort of a demo version, or you could put this into production. And we encourage you to really take advantage of this, because the advantages, as we've covered, are just so great, and we believe that this would definitely be worth benchmarking and considering how you can use it in your own video operations centers. So if you just want to go to, I created a bit.ly link just simply to keep the URL more manageable, but the link is here on the screen. If you just go to bit.ly and then it's easy, EASY -T408. And I'm sure in our follow-up email and all, we'll include this as well. But a very simple form, just fill that out. We give you the option to buy 1 or 2 units, and basically give us a mailing address and a credit card number, and we can get that shipped out to you. So in conclusion, what we talked about today are 3 massive advantages, and that is a 10x density advantage of an ARM-based server running an ASIC video transcoder, that the density, as you've seen, is just overwhelming. For X264, comparing X264, but for the H.264 codec, there's an 18x advantage when you look at it from an energy perspective, energy consumption, and HEVC is even more compelling at 180x. So I hope this was useful, and we want to transition now into questions. So thank you very much for joining us, and please, stick around, because this is usually when the really good stuff happens. So yes, thank you. And Bob, why don't we get started with some questions here?
So if anybody wants, thank you, Mark, Sean, actually, and Darren. That was a great presentation. I think what we can do now, as Mark said, is open the floor to some questions. So if anyone has a question, just put it in the little Q&A, the Q&A box, I think, in your meeting controls. But maybe I can, while we're waiting for people to come up with some answers, I can start. So I'm not sure if this is like a Sean or a Mark question, but maybe I'll ask the question that some other people are thinking. Why would someone use, or can you compare, contrast, or maybe provide some of the differences between let's say an Ampere sort of ARM-based solution versus x86? I guess what are the differences, or why would one use one over the other?
Sure, I can start with that. If Mark has thoughts, he's welcome to jump in. We get this question quite a bit, and essentially, the Ampere processor, as Darren no doubt had kind of gone through, was designed from the ground up to be a cloud native processor. So this kind of gives you this predictable performance. Part of that's our single threaded cores. Part of that's our consistent frequency scaling, which we don't scale like the x86 ecosystem does with Turbo. And this really gives you that rock solid performance across any sort of threaded or process-based workload, which is the vast majority of workloads in the cloud today. And so this is a very, very compelling, predictable platform. If you are a service provider, you would also be interested in the fact that you can deliver, at par, if not greater performance than the best x86 processors out there in the market today for lower power and typically lower cost. So both of those advantages we also have over the x86 industry. One other thing I'd like to kind of just insert into here, I know you didn't ask it in your question, but many people have questions about the viability of ARM software, or sorry, any software running on ARM in the server ecosystem. And for these transcode code workloads, we've tested a lot of codecs, we've tested a lot of frameworks. All of these frameworks are working and running. You can actually go see many of these running in regression on the Ampere Solutions Portal, which is Solutions Portal at Ampere Computing, or .amperecomputing.com. And I think this is something that's also sort of a necessary statement in answering that question, because a lot of people do wonder, hey, will my workload actually run on an ARM processor?
Okay, great. Now, actually, Clifford has a question. It's kind of a one-word question, so it's a software as a question mark. So I'm going to assume that he wants to know, I guess, the Ampere sort of / NETINT solution that we've been talking about today. What software are we using to to enable that?
I can jump in here. Yeah, so as we talked about, in terms of most of our customers are using FFmpeg, and I think that's pretty ubiquitous. And so of course, we fully support FFmpeg. But the point, as Sean just said, is it really there isn't any video encoding software workload, video transcoding frameworks that cannot run on ARM, or certainly cannot interface, that are unable to be interfaced with our solutions. So of course we need to understand a lot more about the specifics of what your environment looks like, but at the end of the day, this is this is not a limiting, software compatibility is not a limiting factor in the solution at all.
Okay, great. I'm going to jump around a bit here. So, potentially another question is, we've talked a lot about the performance of this solution today. Can you guys speak a little bit about the latency, the latency performance of this solution, if it's sufficient for all these new emerging type of interactive applications, let's say like cloud gaming?
Sean, we need to do a webinar on mobile cloud gaming.
We certainly do. There's a lot into the answer to that question.
Yeah. I'll let you take this one, because together we're working on probably the most demanding application out there.
Yeah. So we didn't share latency numbers today. We have been running a lot of workload analysis on that. And it's all good. As anyone who knows, the part of latency also is in quality, which Mark alluded to earlier. And if many people make the trade-offs for lower quality or different encoding algorithms to bring latency down. when you're, and I'm going to pass this right back to Mark, when you're using an ASIC-based solution, I think one of the nice benefits is that you always get a consistent latency, kind of.
Oh, looks like we lost Sean.
I think you kind of faded out
regardless
there.
of algorithms.
Oh.
Maybe that's.
Go ahead, Sean. We lost you for just a minute.
Oh, you did.
Back up 10 seconds. Yeah, back up 10 seconds and.
10 seconds. Oh, I was saying that the part of the whole question here is the actual consistency of the algorithm through the ASIC, and so I was going to pass it back to Mark for further comments on that.
Yeah, absolutely. And I referenced mobile cloud gaming just as a proof point, and we do plan to do a webinar where we will be providing a lot more detail around what this solution can do and how this solution is even being deployed today. And that is the Ampere Arm platform with NETINT VPUs in very high scale mobile cloud gaming. And obviously, gaming is where latencies are most critical. I can only think of maybe virtual desktop is another application where the user experience is just really degraded if latency is not consistent and very low latency. So, we're giving a little bit of vague general answers here, but the point is that this is the solution for any application where latency is a core requirement to the experience, to enabling the user experience.
Okay, good answer. Another question actually we have from Steve is, I guess one of the concerns that people have with sort of really hardware-based solutions is support for future codecs. So can we speak to, I guess how we're going to handle support for future codecs, let's say like AV1?
Yes, we can, Steve. So we've publicly announced this. So our next generation ASIC called Codensity G5 is rolling out as we speak. Now, it will be actually available in terms of NVPUs and ready to purchase and to use later this year. So we're still a couple months away. It's not that you can put your orders in yet. But that is going to be not only significantly more capable, but it will support AV1. And in fact, it is the first hardware solution for encoding. There's obviously decoders in the market, and this will decode as well, but for encoding, that supports AV1 and supports AV1 at a very high standard, very high quality. So a lot of people are really waiting for this to drop, and happy to talk more about that if you contact us, separately.
Good. Okay. So maybe one last question here in the queue. Can you talk a bit about, is this solution, has it been deployed? Is it being used in the field now?
Yes, it has.
Good answer.
Sean, we need to do that mobile cloud gaming webinar.
Yes, we do. Yeah, that's a good invitation to have us back, and
that's right.
I appreciate that. Your patience with my connectivity problem today.
Yeah. So let me, sorry for jumping in here, Sean. I'll let you, talk specifically around, Ampere and some of the, some of your deployments, but just from the NetInt side, which this mobile cloud gaming application we keep referencing is a solution that is really taking advantage of what we presented today. But we are, our solutions are deployed across really a wide range of video workflows, everything from typical premium content, live streaming type services to file-based, to more, you might say, user-generated video sharing type applications, and then, you know, ultra low latency, as in mobile cloud gaming or virtual desktop. So right now we're really seeing growth, you know, really across the board. The drivers for why someone wants to adopt an ASIC solution and an ARM-based server varies a little bit across each of those applications, but at the end of the day, there isn't anybody who doesn't care about driving their operational costs down. There isn't anybody who isn't trying to continuously upgrade the viewer experience, and that means pushing resolutions up. All of that's possible in software, of course, but that means adding more machines. In some cases, there's not room in the data center. You know, there's operational cost considerations. So really, regardless of where you sit in terms of the type of video operation that you run, that you design, build, and operate, this system can benefit you.
Okay. All right. Actually, Philip has a question. Actually, just popped up. So I'm going to read this to you. So, ARM-based servers are nice, but can we use benchmark the T408 in existing x86 hardware?
Sure. And
yes.
we have that data. Yeah.
Yes. Okay. So I think that's it for questions right now. I think we've
all right.
had a great session.
Well, this is let's wrap it up, and you know, I guess thank you everyone for joining. Really appreciate it. We've now alluded multiple times that we do plan some follow-ups. We will be doing more webinars, and we'll certainly be emailing you all and letting you know when you know, there's other webinars coming up in our series. And any questions, again, for Ampere, go to amperecomputing.com. You can learn all about what they do and learn more about their solutions. NETINT is at netint.ca. And yeah, we'd love to hear from you.
Yeah, I'll be over the next few days. Keep an eye out. I will be sending out to all the participants today just a kind of a follow-up email. There'll be a link to more information on the offer that Mark talked about today, as well as a link to the on-demand version of this webinar today, so you can watch it again or share it with your friends. And just in closing here, I do want to thank, in addition to participants, for showing up today, taking the time out in your schedule. Also the presenters, Mark, Sean, and especially Darren for the super quick, you know, jumping in front of the bus there and
You're welcome.
Doing a quick save. Awesome, I really appreciate that. So again, I think we can wrap it right here. Again, thank you everyone today, and stay tuned. We'll send out information on that next webinar. Thanks a lot.
Awesome. All right, thanks everyone.
Right. Take care, everybody.
Okay,
Thank you.
Bye.
Bye-bye.